Welcome to our YouTube channel Incredible Maths. In this video we will see the definition of basis and some examples related to the basis and dimension. So first let us see the definition of the basis. So basis, so to define basis we need a vector space. So let us see that. Let V be a vector space over F. A subset B of V is said to be a basis of V if the following conditions are satisfied. So the first condition is B should be linearly independent. So this we have already seen. So B is linearly independent, and the second one is B spans V. So that is, so notation we can write it as L of B equal to V. So that is, every element in V can be written as a linear combination of elements in V. So the definition is every element in V can be written as a linear combination LC. So linear combination of elements of S. So dimension, so next definition, dimension. So the dimension is the number of elements in the basis. So number of elements in the basis. So next we will see some definition, that is the dimension denote cardinality of B. So some examples. Basis for some vector spaces. So the first one, so let us take V is equal to R. So here by default let us take the field to be R. Okay, so here let us assume F is equal to R. So V is equal to R, that is set of all real numbers, set of real numbers. Now let us write the basis for, okay. So for every vector space we have a standard basis. So standard basis of R is singleton 1. So this is standard basis. So there can be more than one basis. There can be more than one basis for V, for a vector space. So here the other basis of R is 2, singleton 2. So any element other than 0 will be a basis for this vector space R over R. So since there is only one element in the basis, so here we can say a dimension of R over R is 1. It is number of elements in the basis. In the basis we have only one element, so therefore the dimension is 1. So next let us find the dimension of R2. Dimension of R2. So R2, so here also the field is assumed to be R, real numbers. So first we will write the basis. So the basis of R2 is 1, 0 and 0, 1. So this we call it as standard basis. So here a dimension of R2 is 2, and similarly dimension of R3, so now we can say dimension of R3 is 3, so because the basis, standard basis will consist of 3 elements, so namely 1 0 0, 0 1 0 and 0 0 1. So therefore, so this can be generalized. Dimension of Rn is n, so the basis is 1 0, so 0 in the first component and the second element, sorry, 1 in the first component, the second element will have 1 in the second component, and the nth element will have 1 in the nth component. So next we will see a dimension of vector space related to the set of all polynomials of degree less than or equal to n. So we will see the notation. So this notation Pn denotes set of all polynomials of a degree less than or equal to n. So it is less than or equal to n, not less than or not equal to n. Okay, so it is less than or equal to. Okay, so we have to note here. So if we take a set of all polynomials of degree equal to n, then that set will not be a vector space. So degree should be less than or equal to n. So Pn will have elements of the form a0 plus a1x plus etc. plus an x power n, where this a0, a1, etc., an are real numbers. So here also the field is assumed to be R. So this we call as set of all polynomials of degree less than or equal to n over R. Over R means the coefficients of these polynomials will be real numbers. So now let us find the dimension of this thing. So first let us consider P1. So P1 will consist of elements of the form a0 plus a1x, where this a0, a1 are real numbers. So before writing dimension, we will write the basis. So basis equal to 1 comma x. So using these two elements, so we can generate or we can construct any element of P1. So therefore, here say dimension is 2. Since there are two elements in the basis, dimension is 2, and P2 will have elements of the form a0 plus a1x plus a2x square, such that a0, a1, a2 are real numbers. So here the basis is 1 x square. So here dimension is 3. So now we can give numbers. Okay, no problem. So now let us generalize this one. So Pn. So already we have Pn set. So here. So now we will write the basis. So for this base set, basis will consist of 1 x square x power n. So therefore dimension we have, so here we have 1 x square, so n elements and 1 for the constant term. So therefore dimension is n plus 1. So these are the examples correspond to the set of all polynomials of degree less than or equal to n. So now let us see other category. Set of all, suppose if we take V as set of all 2 by 2 matrices over R. So over R means, so we will see this set. So V equal to set of all 2 by 2 matrices of the form A, B, C, D such that this A, B, C, D are real numbers. So now let us write basis for the set. So basis equal to 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So since there are 4 elements in the basis, dimension is dimension is 4. Now let us try to generalize this one. Suppose if V equal to set of all matrices, set of all 3 by 3 matrices over R, so over R, then the basis will be 1 0 0 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 and 0 0 1 0 0 0 0 0 0 0 0 0 1 0 0 2 2 0 0 0 0 0, it will be 1 0 1 0 0 0 0 0 0 0 0 0 1 0 0 0 and 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 1. So there are no other elements. So here the basis will have 9 elements. So the dimension will be is 9. So it is nothing but 3 into 3. So 3 denotes number of rows and this 3 denotes number of columns. So number of rows and this one is number of columns. So therefore we can generalize this one. Suppose if V is set of all matrices of the form M by N whose elements are real numbers, then dimension, number of elements in the base, dimension can be, so this one M times N, so this is equal to Mn. Suppose if the matrices are square, so V equal to M n by n, entries are real numbers, then dimension is n into n, that is n square. So these are some examples related to the finite dimensional vector space. So let us see the definition of finite dimensional vector space. Finite dimensional vector space we call it as VS, DVS, finite dimensional vector space. If dimension of a vector space is finite, then V is a finite dimensional vector space. So all the above examples have finite dimension, therefore these vector space are finite dimensional vector spaces. So if dimension of a vector space is not finite, then V is an infinite dimensional vector space. This infinite dimensional vector space. Now let us see some example for infinite dimensional vector space. Example. So let us take the polynomials p infinity. Set of polynomials p infinity. That means p infinity will consist of all polynomials of all degree a0 plus a1x plus etc plus an x power n plus etc. So where this a0, a1 etc are real numbers. So here basis is not a finite set. So basis consists of 1x, x square, xn. So it's an infinite set. So therefore dimension is equal to infinity. Therefore this is an infinite dimensional vector space. So P infinity is an infinite dimensional vector space. So this is one example. So other example, set of all functions defined on the interval closed interval a comma b. So here the basis set is not finite, therefore it's an infinite dimensional vector. So the content of this videos will be helpful in preparing for the examinations CSIR NET and GATE exams. Okay. So if you like the content of this video, kindly like and share with your friends. Also support our channel by subscribing. Okay, thank you.